There we go. All right, so, and sharing the screen I already did. And I need to go in here, my files. And I'll just upload the file while I'm thinking of it so I don't forget. And I'll show you it. It's already loaded on my computer anyways, but I might as well put it here so you know it's here. You can load it up and follow along with it if you want instead or whatever. I need to go to desktop, Q for homework answers. Hello. All right, that'll be there in moments. So what that looks like is this. So I just have the various answers and solutions and so on set up here for you. Oh yeah, so the first question was how many electrons are there in 1 Coulomb charge? Obviously, you either just know or look up the answer that it's 6.24 times 10 to the 18 electrons. But the better answer, the more useful answer going forward, because it's the kind of calculations you're going to be using and doing and so on, is to remember that one electron has a charge of 1.602 times 10 to the negative 19 coulombs, which is the fundamental charge, the smallest charge possible. It's a very significant thing. So it has more, importance than this 6.24 number in my experience. So in which case, then you just do the conversion where you're like, 1 electron equals 1.602 times 10 to the negative 19. So you have, if you want what, 1 coulomb of one coulomb is how many electrons then, right? So what we're saying. So in this ratio, you can see that you must be dividing by this 1.602 number to get a 1. 1.602 divided by 1.602 gives you 1, right? Going that direction. So that same division gives you the answer of 6.24 times 10 to the 18. Okay, so I much prefer you to, I certainly want you to be able to do this. If it was just a direct question like how many are there, well, maybe you just say I looked it up, I know it or whatever. But like I said, this kind of calculation is important for this course and for going on in science. So that's good to know. I did want to mention a little bit about ratios, actually, this idea of like calculating with ratios. And I said yesterday that I was going to mention various ways that is very useful. So a couple just quick here to describe. If you've ever mixed oil for a 2-stroke engine, like a lawnmower or a chainsaw or whatever, you get a gas to oil ratio. Right, and so usually it's like 40 to 1 or 50 to 1 or something like that, right? So basically you're looking at your can, or like on the back of the oil jugs that you usually set gives a bunch of numbers. It'll say like 50 to 1, then it'll say, oh, so if you had 5 liters, you mix this much oil, and you can have, and so on. It gives you a bunch of numbers, but lots of times the numbers don't really match what's on the bottle. So if you have like a 7-liter tank on a little dirt bike or something, you're wanting to know how many liters, it's not the easiest number to figure out till you realize you can use ratios, and it's super easy, because what makes a 50 become a 1? Can I get an answer to that? You're multiplying or dividing something, right, by something to make 50 become a 1, which of course would be, anybody know?
50.
Divide by 50. Right, obviously, right? So that one's super easy. So it's divide by 50 just because it's obvious, or if you're thinking of it very, very generically, which will help on the next example, you're thinking of it as you're multiplying by the second number divided by the first number. I'm just trying to give you the skills that make ratios super easy, so you don't shy away from them, because it is really handy. Okay, so I've used this lots of times. I used to have a calculator in my shed. I don't anymore, of course, because my phone functions as a calculator, and of course it's like attached to my hip, right? So like everybody's. So yeah, that works nice, right? So then you just do your 7 divided by 50 and you get your answer, right? So this answer is just that 7 divided by 50 gives you the number of liters. And of course, then you have to remember, like, oh, well, then 1 liter equals 1,000 milliliters, right? In which case, you have another conversion that you can think of doing easily. You got this number here of 0 decimal whatever liters, and then you're like, oh, well, I have to multiply by 1,000 to get the number of milliliters. See how ratios even kicks in again, right? To figure out the number of milliliters. Okay, so ratios are kicking butt there. Let's just remind ourselves what we're doing here, ratios. So the other example that I used a ton was when I was mixing mortar. So this is a mortar mix for doing tile work and renovation we did at the house here. So mortar mix to water. And there's certain numbers, and this is the one where the second divided by first really comes in handy, because the mortar mix, it comes in like a 10 kilogram bag. So let's say, let's move that down. Let's make a heading here. It's obvious that we're talking about kilograms for this one. And then the water is in liters, right? And I think it was something, if I remember right, like 4.26 liters of water. It's been converted from imperial or something, right? So it's just an oddball number. So you don't have the luxury of being able to just say, oh, obviously you just multiplied by 4.26 or whatever, because you have weird numbers, right? So people that don't use ratios tend to get handcuffed by either mix a full bag, or you mix a half a bag, or you mix, you know, some easy fraction of a bag, so that you can easily figure out how much water. If you have ratio knowledge, then you can say, oh, you know what, whatever number of kilograms you want to mix, you can just get the value, because the value is easy to calculate. It's just going to be the second number. If you want, say you're starting with a known number of kilograms, say you wanted to mix like 4 kilograms if you wanted, right? Then you know that you have to just multiply by the second number divided by the first number, and that'll give you the exact number of liters that you want. I even went so far as to count, say with half a bag, or maybe I did a full bag, but full bag, you end up with so much mortar, it starts to solidify on you before you're done the job, at least with me anyways. So I actually did it for half a bag. But long story short, if I looked at the number of square feet, because I had 12 by 12 inch tiles, so they were 1 square foot each, so number of tiles basically. So I think if I remember right, this made like, say 32, or I'm gonna say like 36 tiles or something. I'd laid 36 tiles with a full bag, right? So now I had the luxury of being able to say, okay, you know what? I've got, I don't know, 11 tiles worked, cut and ready to go, right? Certain number of square ones, a certain number that are custom cut. So I had my 11 square feet of tiles. So now I was able to easily figure out how much water and how many kilograms of mix I needed. Because here, the conversion, what would the conversion be to convert 11 square feet to number of liters? Anybody do that for me? Remember, you just have to look up here and say, okay, well, what am I doing here? What's my second number divided by my first number? I just had to multiply by 4.26 over 36. Right, I wasn't patient enough there for you guys, but does that make sense? It's just using the ratios. So that would give me the number of liters, right? And then I could take that number of liters and multiply by what? And that'll give me the number of kilograms.
The 4.26 over 10?
Almost, because we're going the other way this time, right? We'd have to look this way. I'll go purple this time. If we're going from this over this way, then I have to do the 10 divided by 4.26, don't I? Right? Second number that I end up at. So super close there. Thank you for trying. It's life's full of risks, and that's a minimal one. You did a good job. I appreciate it. That's the idea, right? So we learned from that, and yeah. So this, I was able to figure, out how many kilograms of mortar to mix, and how many liters of water, and it was like the right amount of mortar for the number of tiles I had ready to go. So it drastically reduced the amount of waste. Because lots of times, if you're not calculating carefully, you're figuring out how much you need, you end up with a bunch of mortar left over, and you don't have tiles ready for it, and you end up with a big pile of wasted mortar, which I had hardly any because I was doing these calculations. So it was like ratios to the max, and it was, it's not hard. You just have to get the hang of it and use it. Notice that it's actually kind of, I wasn't really planning on this. I was getting ready to do tiles, and I just kind of developed it, or started doing this as I was going through it, because I was like, I got tired of guessing and ending up with a bunch of extra left over. So that really, if you're describing, what did you do in physics today? You'd be like, we learned how to mix mortar. The reason I'm talking about that is just to motivate you to realize that ratios are really good. So most underappreciated basic math skill. The rest of this homework here, obviously here we talked about there's so many electrons traveling that are transferring so quickly that we talk about a bundle of them. And then the third question here was how many electrons are there if you got 3.5 coulombs? And so I have all three solutions worked out. My preferred one, of course, is based on this fundamental idea that an electron has this fundamental elementary charge, right? So there's your number of coulombs that an electron is. There's your number of coulombs you have. And then, in this case, we're just dividing by that 1.602 number to get the number of electrons. Or if you're working from the number of electrons in a coulomb, then you can see, oh, I'm going to multiply by that number. Or if you're using the equation, it's along the same lines as the first ratio example, my preferred ratio example, right? Because you're obviously just dividing by the 1.602. Okay, so those are all worked out. Ideally, if you have a full set of skills for this course, you can do any of those methods, right? Like, that should be obvious. Oops, I left a little piece here when I was copying and pasting and making this file. Then this is the fourth question. It says, oh, there's a number of electrons, right? So again, with the known ratio that a one electron is 1.602 coulombs, you just put your number of electrons in and see what you need to do to figure out the number of coulombs. So, I need to multiply by 1.602. So you do. Or divide by 6.24, or and so on. Okay. So I get the draw of this. I do, because it's an equation. Boom, plug it in. It just you're justifying your work that way. But Q's and N's and E's don't necessarily mean something to you in the long run, right? Whereas the idea that one electron is this many coulombs is like a fundamental thing that deserves to stick in your mind more than a Q and an N and an E. Deal? The other big thing, interrupt me if you have questions, as always, please. It's a weird thing for a teacher to say, please interrupt me. But I can't see you, so don't suffer. Let me know if you need help. Anyways, moving on until I get interrupted. Series circuits and brightness and so on, you've had a chance to investigate what the circuits would look like. So I'm hoping you saw that with one bulb it was full brightness, and then with two bulbs they're like both kind of dim, and then with three bulbs they're even more dim, even less bright, however you want to word it. And I would even go so far as to say that maybe you could say that these look like half as bright. They're splitting the brightness evenly. They're certainly the same as each other, and then here they're the same as each other as well. And so the conclusion from this, as far as brightness goes, was for you to definitely know now, if you didn't already get it, but the idea more bulbs are added in series, the brightness of each set of bulbs decreases. And so the conclusion from that would be that they're sharing the energy carried by the electrons. That sharing concept is quantitatively, if you remember that terminology, number-wise, right? Quantitatively confirmed with the sharing idea here with voltage, because we've got 9 volts are given to the electrons, the +9, and then we've got a -9, right? -9 is the 9 joules being taken away from the electrons, used by the bulb. Then in the 2 bulb circuit, you've got the +9, you've got -4.5, -4.5, like half each. And in the 3 bulb case, we've got the 9 volts, and we've got the 3, sharing evenly that way. So I've got that worded there where the 1 bulb gets the entire 9 volts. Notice I'm adding here that volts is joules per coulomb, right? With 2 bulbs each get half, so it'll be 4.5 each. 3 bulbs each get 1/3, or 3 volts each. Okay, so that's the knowledge conclusion to do with series circuits. So that may or may not have changed your modified your understanding of this. I know for a fact, I don't want to say any names, but I know that sometimes people would maybe think that for example, in the 3 bulb circuit, maybe the first bulb would be the brightest, and then the next bulb would be a little dimmer, and the third bulb would be even dimmer. But that's not the case. They're actually just sharing equally. Notice I've said more clearly in my answer here that we've got identical bulbs. That's important. We're going to come back to that soon. And these are identical bulbs. They're sharing the energy evenly. So they're all the same brightness. Okay. And then with parallel circuits, I think this was already on the slide. You've noticed the stuff that I uploaded, but so there's only 2 of them made here, but yeah. So the 9 volts, and of course the one it's the same circuit series, right? But if you did the 2 bulb and then the 3 bulb, you'd see that they're always the same brightness. They always get the same amount of energy. So the way you can explain that is right here with the idea that each electron only goes through 1 bulb. So if you're looking at the path, the electrons would take here, electrons either go through this loop and drop off their energy there, right? Picture an electron or a group of electrons, of course, with 9 joules, right? So that electron with 9 joules can come along here. Let me just group that together. Is my keyboard? I think it is. Yeah. So this electron that picks up 9 joules, so it had 0 joules, now it has 9 joules, right? Picked it up, comes through, and it goes through this bulb, drops off 9 joules, comes back to the battery, right? Or at this little junction, the T junction here, it could have gone this way and gone up through here and dropped off 9 joules, and then goes back to the battery, right? The electrons aren't going to like swim upstream here. Like there's a push in this. There's a push up this way, right? And so that push, ends up effectively pushing kind of both ways on those circuits there. So yeah, this circuit here. Let's go for a different color. So let's go red, right? So or you're going to go up through that one, right? So yeah, they're only going through 1 bulb ever in this type of simple single bulb parallel circuit, and so they drop off full energy in each one. That's why the same brightness in each one. Okay, so if you're expecting, this one to be the brightest, and then this one less bright, and then the third one even less bright, you've corrected your predictions and your ideas based on seeing what the circuits do in the simulation. Okay. So if we were in class, then you would have had a chance to do this with wires and bulbs too, and you see the same thing. The only problem with real circuits is sometimes the batteries start to die, in which case in the series one in particular, actually the parallel one too. Sometimes in the parallel one, as you add more bulbs, they actually get less bright because the battery starts to not be able to provide a full amount of current. There's actually internal resistance inside of the battery itself, and so some of the energy actually ends up getting dropped off inside the battery itself as it tries to push more and more current. And that's actually why batteries get hot. If you've ever felt a battery that's hot, it's because it's trying to push so much current that it actually, some of the energy actually gets used in the battery chemicals itself. Your phone, you probably felt it hot. Lots of types of batteries can do that. Yeah. So that is a very thorough take-up of everything from yesterday, and all of that is posted for you and good to go. Any questions right now? Both things is. All right, no one's keying their mic, so let's keep going. So we're looking at voltage some more, and so that was very, very much a reminder of things that hopefully you've seen before. In which case, great. If not, then, well, you know what? You've seen it now and you're good to go, right? Everybody's on the same level playing field, regardless of what they saw in grade 9. I'm hoping. So we're talking about electric potential energy and then the equation and calculations to do with it, right? So I just want to try to help you think of how electrons do this, how they, where's my homework one? I just want to, yeah, there it is. So, we think of, the better answer is probably what I said yesterday about how, you got a bunch of electrons single file that are getting pushed through the circuit. And as they get pushed through a load, the load uses energy from it, right? That's a simpler way to think about it, because then you can even talk about alternating current, where if the electrons get pushed the other way, then the electron goes the other way through it and still drops off energy as it gets pushed through. It's the actual pushing that transfers the energy. We do like to talk about the potential energy that they carry, and my associate teacher actually in Rockville, when I was student teaching there, asked me, like, how does an electron carry energy? Like, what does it look like or whatever when it's carrying energy? So picture an electron, or a group of electrons, of course, right, that has energy, and a group of electrons that doesn't have energy. What's the difference? How do they look? What's the, whatever. And so an analogy you can use to help visualize it is picture like a heavy object up on a top shelf and the potential damage it can do to your foot if it falls off the shelf and comes crashing down and hits your foot. In that scenario, we're talking about gravitational potential energy, right? So a heavy object on a top shelf has gravitational energy relative to the lower position at the floor, or where your foot is. And so it has energy, it's carrying energy. Does it look any different? No, it's just, it has energy because of that push, right? That push is going to push it down to the floor and it's going to transfer energy to your foot. So that helps you think of, should hopefully anyways help you think of the idea of electric potential energy. So I've flipped it sideways just so we don't think that gravity is involved here. But if you had a large buildup of electrons on this surface, then this electron would have a push to the right, right? And so it, as it goes to the right, would accelerate towards your foot. If your foot was on this surface, and it would hit your foot, just like this mass would, okay? So there's a force of gravity on mass, and so it has energy on the top shelf. There's a force of, there's an electric force. It's actually voltage, electromotive force, EMF, right? That's all the same thing. It has a force on it due to the electric fields, which we're going to be talking about a little more soon too. But that's how they're embodying or carrying that energy, is they get pushed as they go. All right, so that hopefully just helps you understand a little bit with the idea of how an electron can actually even just carry energy in the first place. Possibly questions you might not have even thought of asking, right? It's just I've been asked these questions along the way, and so I've been forced to think about them, and I think I understand it better for it. So I'm sharing that with you. Yeah, so it's really energy due to its location, just like with gravitational potential energy. Okay. I do like the idea of the push single file through the circuit, though. It really helps understand things. So combine those two and get the idea in your head. All right, so here we go. Another equation now. I want to highly encourage you to think of these equations based on the concepts they're representing, rather than just a bunch of letters. Okay, even the Q equals anything. Just got to remember. Okay, so the quantity of electrons. It's the idea what things represent. I won't go into that one anymore. We've already done it. So we know the concept, right? We know voltage is the electric potential energy per coulomb, right? And I've got it sort of sit there as like the change, or set there as the change in electric potential energy per coulomb, but it's the energy per coulomb that it has. Oops, that was what I meant to do. Let's grab a pen first. There we go. I'm just going to finish my quotes, just looks better. So it's the change in electric potential energy per coulomb. And when we're talking about the change, remember that's energy that it picks up from the power supply, or it's energy that it drops off in a circuit. And that's where you get positive voltage or negative voltage, right? And I'm using EPE sometimes as a way to remind you what voltage really means, right? That voltage really means electric potential energy. I should have per coulomb there, though, shouldn't I? To be totally correct. In this one here, it's actually okay, because we're actually just looking at the energy picked up. Per coulomb is still a little bit more specific. I will leave it. So what would be a logical equation for this then? We've got symbols. We can use V for voltage. We can use delta E for change in electric potential energy, and we use Q for charge. If we're saying the concept is energy per charge, it's like same as saying like kilometers per hour for speed. It's a very simple equation. So I don't want you to think of this as a stressful course where you're trying to memorize a bunch of letters and their arrangements. You can use the concepts to help you understand the equations at a fundamental level, and makes it easier to remember them and use them. Okay, so that's the box there. There is a handout sheet for this one, of course, I'm hoping. So there's a box to fill in there for this part here, and then little boxes for each of those. Sorry, I should have mentioned that earlier. I'll give you a second to get that going. All right. Just a brief bit of a calibration to do with this, like just like when I was talking about like that obscure number of coulomb or electrons in a coulomb and so on. The original number led to all the rest of the numbers, right? So now we're saying 1 volt is when 1 joule of work is done on 1 coulomb of charge, or 1 joule of work is given to or dropped off by 1 coulomb of charge. So that 1 joule was sort of a known amount, and then the coulomb, like that was determined by the number of electrons it would flow when 1 amp flows for 1 second, and so on, right? But so this definition makes the it kind of goes towards making the number of coulombs be kind of obscure, right? Because the joule was known, and I don't know, you know what I mean? Does that make sense? Sort of. It's not that critical anyways, but yeah. So anyways, hopefully that's enough time for you. We've got volts equals, volts equals change in energy per coulomb or per charge, per coulomb of charge. So I have a spot for you on the handout to write this example. So I have it like this. I can see where I'm going here. I've got my background on there. If I do just the page, Photoshop, no. The background's shooting me in the foot again. That's okay, they're fun. But yeah, there's a space there underneath voltage and whatnot, and those blanks for you to do. So it says, the example here says how much work is done if an 18-volt battery is connected and 64 coulombs of charge moved through the circuit. So how much work was done, I guess. Good, right? If I have to change all the past tense. Was done if was connected. And this is why English is a hard language. This wouldn't even sound bad to someone who doesn't understand English, but how much work was done if an 18-volt battery was connected? Changed the other tense and 60 moved through the circuit. Anyways, gave you time to write whatever you want. So what are we given? Well, of course, we're given the voltage is 18 volts. We know that means that 18 joules is carried and delivered by each coulomb, right? 18 joules is carried and delivered by each coulomb. So it's 18 joules per coulomb. This, what I'm doing here, this is just emphasizing, reiterating, repeating to help drive that firmly into the brain, okay? So I want you to have a really, really easy, full understanding of what voltage is. Plus, you're told that 64 coulombs went through the circuit. And without even using a formula, I think it should be pretty obvious, right? If each of those 64 coulombs is delivering 18 joules, right? If there was only, say, 2 coulombs, or let's make it even easier, if only 1 coulomb went through the circuit, then of course it would have delivered an 18 joule package of energy, right? 2 goes through, 2 18 joules go through, 64 coulombs go through, then we got 64 groups of 18 joules going through. So I think the concept, I think maybe you can see that you don't even need an equation for that. You can just be like, well, each one delivers 18 joules, so duh, this is pretty simple, isn't it? Right, so let's just arrow that in here. So each delivers 18 joules. So obviously we're talking about like 64 times 18 gives us the number, the amount of energy, right? So how much work was done? I have to remind you that means like energy transferred, right? That's from grade 11. So this would be whatever number, right? This would be set number of joules. So that would just work out. What we're looking for, like I said, is work done, energy transferred, and so on, as I just reminded you of there. So the concept is strong here. Like it should be pretty clear. It's like if you go to a store and buy 1 chocolate bar and it's $1.12. Well, if you bought 6 of them, it would be how much money? 6 times $1.12. It's the same concept, just a bunch of the same thing. So when you use the equation, it ends up doing that for you, of course, right? But it looks more mathematical. You're just putting things in places. So obviously the 18 is going to go in for voltage. The 64 is going to go in for Q. Like that. Right? Mathematically, of course, we're multiplying both sides of the equation by the 64 to mathematically solve this equation, which gives, of course, the logical answer, which we've already sort of realized because we're thinking about this instead of just memorizing a new equation, right? So we end up with 18 times 64, giving us 1,152 joules, right? And I have it listed in multiple spots on this page now, right? Each of the 64 coulombs carries 18 joules, which is why this makes sense, right? So it's in multiple spots there, but that is from grade 11 physics, actually. So I reviewed grade 9 stuff yesterday to basically lay the groundwork for this making sense. I hope it's working for you. I didn't want to just jump right into a voltage equation in the first grade 12 physics lesson and review grade 11 stuff, because you might have been saying, what are we talking about? What's voltage? Who? What am I looking at? So do I need to, are we good there?
I think so.
Been enough time. The other pages here, I just have copied in some information from the textbook, the grade 11 physics textbook. But instead of being the water circuit, it was like a ski hill. The idea of energy being given to a mass and so on. But they have the equation, and they have a worked example. It's actually the exact same numbers. I would normally, these days, I use a different number example, and then you can, but this, you can see how the textbook shows it. Anyways, it's very similar. It's nice to have two different examples worked rather than the same one, right? But oh well. So the homework page quant numbers are there, and I've got a solution set already worked out, and I'll post that as well, so you can sort of check your work as you go, see that everything makes sense. Okay. Right now, I seem to have enough time to do those homework solutions in full for you. I'll try to keep doing it, but no guarantees. Especially if we end up going back into the school, because then I have to cover someone else's class and all that. Makes me not have as much time, but we'll see. So that's lesson number 4. Lesson number 5, or I'm just gonna keep going here, of course, but they're not full lessons, so don't think of this as like a number of lessons per day. I just have them sort of chunked into files to organize them. But why don't I have that? Did I move that by accident? I feel like I modified this file by accident. I'm just going to load up lesson 5 again, because shouldn't have started with that, but I might have saved like that. It could be just an introductory. More just for, oh darn it, I just unplugged the mic. Hopefully my audio is back, because I just unplugged the mic instead of the keyboard. What did I want to do? Plug in my memory stick.
We could still hear you.
You couldn't for a little bit though. All right, so this makes more sense to me. So current, definition and measuring and dangers and so on. It's the title page that I normally start with, right? So if we're looking at electric current, just to remind you, you're probably not, I don't think you have a handout for this one really. Your handout, next one is going to have electric current with an I and so on. It's going to be the one with the equations. So you can really wait a little bit until there, but it's a measure of the rate of flow of electrons past a given point in the circuit, right? And it's measured in amperes. So this is sort of fluff a little bit, just ideas. And so the lesson 6 is the one where you have a handout for. Anyways, so it's measured with a device that measures current, and it's actually called an ammeter. So amperes, amps, ammeter, you can sort of see the connection between all of the different words. And you're certainly welcome to jot this down as well on that handout that you do have. So the devices look similar to a voltmeter, but they're actually measuring how much current goes through the circuit instead of just measuring the amount of voltage that energy that's dropped off or whatever, amount of voltage. So when we're measuring current, the ammeter needs to have electrons actually flow through it. And so it needs to have them flow through it and not slow them down. And so it needs to be connected in series with circuits. So it should say that somewhere. Essentially, allow electrons flow. Oh yeah, you can't let it flow. You can't let it be hooked up so that electrons can just go through it and not through something else, because there wouldn't be anything to slow it down. Their ammeters are designed to not slow electrons down at all, right? So by definition, if you hook up an ammeter directly across a battery, then there's nothing to slow electrons down. They'll just fly through that little loop. It'll be a short circuit, and you will cook that ammeter. So a load is needed, of course, in a circuit, right? We know already, to stop things, stop too much electrons, too many electrons from flowing. So this should kind of make sense based on what we talked about yesterday. So if you had a battery and then a switch and then a light bulb and then an ammeter all in a loop, of course, you've got a series circuit that would look like that, right? In reality, it kind of looks like this, right? You have a meter, like a digital multimeter or whatever, and you're hooking, to one side of it and then out the other side of it through your battery, through your bulb, and so on. And so you can see that complete loop where the electrons would go through the device, around, and through the bulb, getting pushed along the way. Okay, so that's how ammeters look when they're used properly. The never do this, of course, is this part here. If you hooked up an ammeter like this, then electrons are going to get pushed from this negative side here. Remember, the little one's the negative sign. So electrons get repelled from the negative and they push, and they'd be like, ooh, check this out. I got this really easy path to go back to where I want to get. And so the electrons would just loop through here without bothering to get, slowed down by this bulb. And so that would be on fire, or not. It's not actually as exciting as it sounds. Just the meter just stops working. So I always tell students that in case they're thinking it would be exciting or something. Want to try it. But yeah. So there you go. Quick story to do with that. Some meters can handle it. I was at a friend of mine's cottage trying to troubleshoot our boat not starting, and I wasn't sure if the battery had full voltage. So we managed to get to their cottage, and my buddy's father-in-law actually had a meter, so he brought it down. He said, "Oh, it's good to go there, Greg. I wanted to check voltage, right?" And he says, "I got it in the right setting." So it was a pretty complicated, like, electrician's digital multimeter. And he said, "It's all set to go." So I went and put it on the battery, and I could feel it almost like magnetically sticking to the battery posts. It was sparking and whatnot. And I was like, this doesn't seem right. So I look at it, and it was set to measure current. And so it was exactly like this, dead short, connecting the meter directly across the battery. And so I handed it back to Marty, the father-in-law, and he's like, "Oh, sorry," and put it on voltage, and I checked it, and the voltage was fine. But I was seriously thinking that it had destroyed the meter, but apparently it was a high-end electrician's unit, and it was designed to be able to handle that amount of current that rushed through the circuit in the ammeter. But anyways, so if you're get into using meters and stuff like that, that's something that you got to watch for. So just quick little fluffy things as well, more about this, like the idea that that current is what really kills you. So an electric current of about 0.001 amps gives you that buzzing, tingling sensation. If you've ever gotten a shock changing a light bulb or whatever, that you feel that buzzing vibration in your hand. It's like 0.001 amps. Household circuits are designed to carry up to around 20 amps. It only takes 0.001 to feel like a shock where you get startled and you yank your hand back if you're lucky. If there was a direct current through your body, then of course it's a different scenario, right? And they'll talk about that shortly. 0.05 to 0.15 causes muscles to contract and convulse out of control. So if you grab onto a handrail that happens to have an electric circuit hooked up to it by accident because it grounded out, something malfunction or whatever, your hand grips the handrail and you can't let go, and so that current's going through your body the whole time. A current as little as 1 amp going through your chest, through your heart, will stop your heart. And remember, there's 20 amps available, 15 to 20 amps available in household circuits. So the tingling of it just going through your hand is kind of startling enough. But this is the deadly stuff. And so you're not talking about much current at all. And it's dangerous for humans if that's the case. You actually end up with like an entrance wound. You can see in this picture here, it's gross, but you end up with an entrance wound and an exit wound. So this person touched an electrical wire and was, the electricity went through the hand and jumped out the other finger, causing burns. And it can be 2 different spots in your body even. It can go like, if you touch with your left hand, it might go out your, if you're lucky, it would go out your like left foot, in which case it would have like skipped your heart, maybe if it was stuck to the outer side of your body. But it's more likely to actually go through your spinal cord because your spinal cord actually conducts electricity really well. And well, yeah, so scary stuff. You got to make sure to not have electricity trying to go through your body. So this, I'm talking about current and how it's so dangerous, right? So little current can kill you, but yet all you ever hear about is high voltage being danger, right? You see this high voltage, high voltage, high voltage. But of course, remember the voltage is the thing that's pushing electrons to make them go, right? And so the more of a push, the more current there will be, and the more dangerous it'll be. But it is possible. You've hopefully had a chance to play around with things where you have high voltages that aren't dangerous. Tesla coils are one for sure, and the Van de Graaff generator is another one. So the Van de Graaff generator we have looks like this. It goes up to like 500,000 volts. I think it's around 350 normally, or 400,000 volts, but it's a huge amount of voltage, but very, very little actual energy stored up, where it's like a lot of energy per coulomb, but not actually a lot of energy, right? And so it can't push a ton of electrons through you and hurt you, at least not to kill you. It kind of hurts when the spark jumps to you. So just to clarify any confusion there, if you think of like high voltage, being dangerous and so on, there's just a subtle difference there where sometimes you got lots of voltage, but not a lot of current available. Anyways, so I had some video links here of electrical wires burning and what happens, things like that. Do you want to see those, or I feel like it's kind of not really critical, but it won't take long. Need those two. So electrical wires. Oops, my keyboard. Ah, darn it, my keyboard's not hooked up. Struggle. Where's burning? Did I type that in right? Yeah, there we go. So just to picture what happens when wires have too much electricity going through them, too much current going through them. Up here. Hopefully. So that's a hydro wire. If you're a TikTok fan, you might have seen that one already. But the point, so much current goes through, the wires actually like melting, glowing. Top 5 dangerous. I'm just going to type in top 5. Typed in. Or was it the number? Ah, darn it. So when we're learning about electric fields and things like that, get a little more life or visual experience through videos, at least, as to what that can look like. So what you have there, and you'll see it in a couple different ways, is there's scribe voltage here, and I'm going to try and just pause it on a time where there's a loop. But you see once in a while there's like a loop, a very obvious loop. And so there's actually what's called a plasma, formed there where electrons are free from their atoms, and so they conduct electricity really well. It's like the fourth state of matter, solid, liquid, gas, plasma. And so the electrons are actually rushing through this path to the other side where they're trying to get pushed to. And so that's a circuit, basically, through the air. And that plasma is really hot, so it rises. And yeah. You don't want to be standing near that. So people are like videoing this probably in their neighborhood somewhere, like, that's probably not good. Another one here. Eventually it gets super bright. It's like it's daylight out. I can tell it must have been really bright because the video is all dark, right? And eventually you see these wires along the side of the road all the time, and they just look so innocent, right? There is a lot of danger in those wires. If this was happening in real life and you're watching this, by the way, you could damage your eyes badly by watching that. That's brighter than like the surface of the sun, people would say, because it's so close to you, of course, right? This one's cool. It's a branch across two wires. You can hear the hissing noise. It's the liquid in the branch, like vaporizing. And then eventually it gets to be such a good conductor that the electricity zaps through it, vaporizes the wood, and then the plasma from the smoke giving off. Anyway, that's a big current, big circuit going through the air again there. Pretty cool. This is, I think, someone with a fishing line maybe or something. That's extremely dangerous if that's what it was. Okay, I can't really see in the video totally, but I think someone's casting a line or something, and then it touches the electrical wires. And so the current actually wants to go between the two electrical wires, right? So the wire went across the two lines, connected the circuit, and then that circuit like continued as the plasma sort of moved along the area through the air. But, wow. Oh, and this is an example here where like a power line goes down, right? And so it's bad enough, it looks dangerous enough. But then you come along 5 minutes later, everything just looks sort of normal, right? And you come walking in, trying to see if anybody needs help, and all of a sudden that happens beside you or something, and you're like, oh my God. Yeah, so be safe, don't go near stuff like that. That's basically what that was about. Anyways, just neat. So, of course, we had we're going to look at making circuits and so on. Let's skip that part. But basically, later on, you'll be able to look at how much current flows and so on in a different lesson. So I'm going to skip that part for now. So that was lesson 6, right? Right. No, lesson 5. Lesson 6. Lesson 6, current equation. All right, here we go. So you have a handout for this one, electric current, and it's probably the same as what we had before. But oh yeah, this is the technical definition part, right? So the conventional or the official technical definition, if however you want to word it, is current is the rate of flow of positive charges past a point in a circuit. And I'm just going to go over to here. I'm going to type in. I'm going to point out that the new version of the program, I don't know if the old version that I put the file, posted the file of has it or not, but the new version, Kayla pointed out to me yesterday, was asking about it. Loading. Lab. There we go. So if I make a quick circuit here, and people would usually think of the logical idea of flowing electrons, right? So you got electrons flowing. So this is the negative end of the battery, and it's repelling or pushing the electrons through the circuit. And then so that pushes this one to the, each one pushes each one, and then eventually one gets pushed through the bulb and the energy gets transferred. Okay, so that's the kind of understanding I want you to have about electricity. Notice over here that you can say, oh, let's think of conventional current or like theoretical current that physicists talk about, and it shows current the exact opposite way, right? So this is electrons. This one here is electrons flowing, which is reality. Before people knew about the structure of the atom and that it was actually electrons going around, they basically took a guess and said, well, it's positives flowing around and in a circuit. And centuries literally of work and development of equipment and schematic diagrams and however you want to think of it, right? There's all this work done based on the idea of flow of positive charges. And so they stuck with it. Yeah, it just seems kind of ridiculous, I know, but the rate of flow of positive charges past a point in a circuit is the technical definition of electric current. My other slide that I must have closed, oh, there it is, number 5, way over here. I would have said earlier on in this one, of course, that it's a measure of flow, rate of flow of electrons, right? So this one's like reality, right? I won't bother, but that one's like what's really going on. And then the conventional definition is the flow of positives. Now, luckily, when they say the flow of positives, they're talking about like a positive charge of the exact same size. And so it doesn't actually make for any functional difference. So I'm going to paste that one in there too. So it's really the rate of flow of electrons. I'm going to say it's really. Really the rate of flow of electrons. Of course, know that, but they didn't know it at the time. Originally talked about. So that's this part here, right? That's all written down for you basically, but you've probably been jotting some points down about it if you want to try and remember this stuff, but electricity was discovered and studied long before the structure of the atom was understood. Hundreds of years later, it became obvious that the positives were locked in the nucleus, but hundreds of years of development of things was already done, right? And so functionally it doesn't matter which way charges are going. It really doesn't matter. And plus, scientists are stubborn and so on, so they just kept it the way it is, even though it's pretty silly. So they try and make it seem less ridiculous by referring to the direction a positive test charge would go. So if you put in this circuit here, if you put a positive test charge in here, which way would it go if you theoretically did that? And of course, it would go the way the red arrows are showing. In reality, of course, there's negative actual charges, electrons, going in a circuit. So that is a little dose of reality for you, I guess, but it is what it is. Either way, you've got the same equation. We're talking about charges per time going through a circuit, right? It's the same as like kilometers per hour. It's like kilometers over hours, it's charges over time. Okay, so you've got charges Q over time delta T. So I'll leave that with you for a little bit. All right, is that enough time for that page? I'll know otherwise. I'll know if you tell me soon here. So of course, we're going to refer to electron flow, right? Because it's actually what's going on. So I will quite often refer to electron flow. But now basically you're going to start to think of it two ways, right? You're going to think of current as flow of positives and electron flow as flow of electrons. Okay, so they're the same thing essentially, but obviously physically very different things. But they effectively do the same thing in magnetism and electric circuits and so on. Okay. But electron flow, which is of course reality, I want to kind of say, you know, that equals flow of positives or current, right? So equals, I don't want to necessarily say equals, but you get the idea. Current is flow of. So they're equal but opposite, I guess you could say, in direction, right? So let's put versus here instead. So electron flow, which is reality, versus current. Flow of I'm gonna say IE actually instead of in quotes because the quotes make it sound like it's fake, right? Mr. Robert's been making fun of me lately of I have a cart in 124 that is labeled on the side and it's physics. It's a physics cart. And physics is in quotes. So Mr. Robert's been making fun of me that I labeled it that way because it's like it's not actually physics, I guess. It's in quotes. But anyways, so electron flow is reality versus current or flow of positive test charges. And you know, these are kind of the same, but just opposite direction. Right? I kind of want to say like they're functionally the same, but opposite directions, if that makes sense. Okay. So you now are aware of the ridiculousness of current in physics, science in general, being thought of officially as flow of positive charges. On behalf of all physicists that were made that choice, I apologize. I wasn't part of the choice, though. Okay, so next thing, let me know if you need more help. If a 9-volt battery is connected to a light bulb for 30 seconds and the current that flows is 3 amps. Questions. How many coulombs of electrons went through the circuit? And then part B, which is a review of the voltage work that we just looked at, how much energy was used by the bulb? So is this where, it's the first time you've ever seen this, so is this a case where I just start showing it, or am I waiting for you to try it?
Could we try it first?
Try it.
The danger, yeah, in a class setting, I for sure would give you a chance to try because I'd be able to walk around and see if people are having success, but don't let me sit here for 5 minutes and you get nothing done, of course, right? So if you're stuck, ask for help, basically. I can show like the given, okay? Yeah. So of course you're given those things and you're asked for, so I'll just show that part. I guess that maybe shows a little too much there. Oh, well. Is that enough time for A at least?
Yeah.
Yeah.
All right. I equals Q over delta T. Of course, we know this new concept that current is just charge per time flowing through a circuit. Plug in the 0.3 for the current and the the time for 30 seconds, right? So that's the other thing I should have put in there for in the given. So I'll just drop that in. Delta T equals 30 seconds. Notice that amps, for example, this is like coulombs per second, right? So if this was given in minutes, then you'd have to change it to seconds, right? It's like that System International SI units thing where it's like meters, kilograms, and seconds and so on. But it's in seconds, given in seconds, and you need it in seconds, and it's all good. So you put your 0.3 amps, which is coulombs per second. Let's go back to this, maybe remind ourselves here. I didn't emphasize it as much here, but on this page here, this is coulombs per second, right? That's your SI units. Also just focused on this weird positive flow of charges business. I forgot to emphasize that as much. So this is coulombs per second, flow of charges per second. And of course, this is your coulombs and this is your seconds. So dimensionally, units wise, it should all make sense. Of course, we're just going to multiply both sides by 30, end up with the number of coulombs being 9 coulombs that went through the circuit. All right. So you're like, oh yeah, that's great. And then in the homework, of course, if this is a separate lesson from the next day or whatever, you would have looked at voltage and the previous day, and you'd be like, oh wait, energy used by the bulb. Like you have to really get to the point where, in order to have this section of this course not be confusing and frustrating and so on, you have to really recognize things like this, where it says energy, you have to automatically be thinking, ooh, that's to do with voltage. So this is like keys to success here. Don't just think of it as a bunch of V's and Q's and I's and T's, right? Concepts are important, okay? So energy is to do with voltage, and so that's why I have a little note there saying it's, obviously this is an application or review of the previous voltage work. And so the concept of voltage is energy per charge, right? Voltage equals energy per charge. I'm going to write that actually first. Oops. Not good enough. So voltage equals energy per charge, right? So that concept is like known. And then the formula to do with it is like V equals delta E over, this is just a V. I'll go with a different color here. This is just your V, and then this is your delta E, the amount of energy that's been transferred, and this is your Q, so it's just really trying to connect the dots here as to what things look like and so on. So I could do it that way, or I could, of course, go with the equations. I'm going to reveal that other one in a second. Okay. So it says how much energy was transferred. Well, the key is we have this energy concept here, right? That's joules per coulomb. It's literally 9 joules dropped off or picked up by each coulomb. So the 9 goes in, and then it was actually 9 coulombs went through the circuit. So that's your Q, and then you multiply both sides by 9, and you get your 81 joules. Okay. So I feel like maybe it might make sense for us to do this part afterwards. Bump this guy up, where it kind of made sense just to go for it, right? This little blank here is the idea that, very logically thinking of this, if we had 9 coulombs went through the circuit and each one carried 9 joules, you got 9 sets of 9, right? You got like wheelbarrow loads arriving with 9 bricks. You got 9 wheelbarrow loads. You got 9 groups of 9, right? That's mathematically very, very easy, very logical. So you with me on the obviousness of that? I need you to be with me on the obviousness of it, rather than just thinking of it as a bunch of equations that spit out a bunch of answers that you know if they're right by looking in the back of the book. Rather, I want you to know they're right because it just makes sense. Like 9 groups of 9 joules of energy dropped off. Of course, it's going to be 81 joules. Okay, so please pay attention to that. The idea of energy. Ooh, that's voltage. Oh yeah, they gave me the voltage information. Oh yeah, I know the concept. And that carries you through the questions. That's going to save you from physics equation soup, if you will. Right? Where you get too many equations that you don't know the meaning of any of them, and it makes it impossible to piece it all together. This makes it possible if you know the concepts. So this is just the textbook pages. There's a question that's worked out, a different example. That's good. So we've got 120 volts. So right away, as soon as you see 120 volts, what are you starting to think? Just think about it a little bit. What is that telling you? Somebody, please.
The energy per charge.
Yeah, each coulomb of electrons. You're not necessarily going to write this down every time, but each coulomb of electrons carries, right? Drops off, picks up, whatever, 120 joules, right, of energy. So, later on when it talks about the amount of energy, you're already kind of ready for that, right? The first things you're going to look at probably, the amount of charge, right? So looking at this many coulombs per second, right? And it goes for this many minutes. Well, watch for that. You have to change that to seconds, of course. But yeah, you're going to figure out the number of coulombs that actually go through. Then you're going to say, oh, well, each one delivered 120 joules. So it's functionally the same question, except it gave minutes. So if we look at it together here, you can see they've got their current equals number of coulombs per second, and they have the seconds converted to minutes. They're not super clear about it, but I would prefer to see it written off to the side where you'd be like, oh, I'm given delta t equals 2.5 minutes. And then you're like, oh, let's multiply that by, let's multiply that by 60 to get, the number of seconds, 150 seconds. And then, of course, later on, you're putting these things into the equation, right? So that's down here. So this is your I equals Q over delta T. There. So we put the current value in, put the time value in seconds, multiply, and get this many coulombs went through the circuit. Heater down a little bit here. So that many coulombs went through the circuit, and then the idea of, well, I don't like the way they're doing this either. So this part here, I see what they're saying. So you can solve for Q algebraically first if you wanted, but who cares? It doesn't matter whether you're solving algebraically for the variable or plugging numbers in and solving. So they're saying substitute in, then mathematically solve, or mathematically solve for Q, and then plug numbers in. I thought they were doing the voltage stuff there at first. So that part should make sense as you go through, except for the organization, I guess. And then, of course, they get to the idea of the energy stuff, right? So if we want the energy, right, strategy, find the change. Well, do with energy anyway. So voltage equals energy per charge. And so we're given that voltage, and we know how many coulombs actually go through. Each one's carrying this much, right? So this is the 1,440 coulombs go through, each one carrying 120 joules. And so it just multiplies and gives you the value. Okay. So that'll be posted, of course. This is another question, or is that the same one? 30 seconds, 3 amps. Sounds familiar. Oh, it's the same one. Yeah, it's the same one. It's just my handout. In order to print this handout, I had it printed on a separate page to be able to print it and give it as a handout. So on the bottom of this is the questions that are assigned for you to try and get through here. So notice they gave you the current and the time. So as soon as you see that, you're going to think, oh, well, I can figure out how many coulombs electrons go through then. I just change that to seconds first and figure out how many coulombs go through. And then it says, if this much work was done, you're like, work was done. What are they talking about there? Work was done. They're talking about energy, right? So this is how much energy was delivered. let's put it in there, energy delivered. So that's how much energy was delivered. Well, that's part of a voltage equation, right? Where you're looking at voltage equals delta E over Q. And so, you know, they're actually asking what's the potential difference. Potential difference is voltage. So you can see in the end, they're going to ask, what is this number, right? They've given you how much energy goes through the circuit, and then this one you will have figured out first, right? So based on this information here, you're going to get Q, and then you can put Q into the voltage equation. It's just a little bit different because we're solving for the voltage instead of solving for how much energy was transferred, and so on. Okay, so those can be a little bit, the way they've done this, they don't have just straight out current questions. They have voltage laced in with it too. I don't like it that way personally. I prefer to have just some current ones first and then some voltage ones, but certainly you can think of this part A, right? Is straightforward, just current stuff. And then part B, the purple part there, was the voltage review. So what do you think of that? So I was thinking that that would be it for today. Seems like maybe I should probably go. Let me just see what I have as another. You're gonna need to have some time to try that though. Just give me a second here. Desktop. That is my next one. Current measuring, current equation, electrical resistance. Oh, that's probably just a concept one. We could probably do that one too. Just some of these are just easy review of ideas, right? Of concepts from previous classes, grade 9 and grade 11 physics. There's one of these. The next one is more to do with like a bigger investigation, so I won't do that because that'll take up too much time. But I bet I can probably, if this is what I'm thinking it is, get it done. So this is very much just a concept, not even equations at this point, okay? But I just want you to be familiar with the idea of it, so that when we do the investigation and so on, so the terms that you hear in electricity, right? Voltage and current and so on. Resistance is inevitably one that you'd end up hearing about as well. So I just want to look at the ideas of resistance, and it's going to be quick just to show you so you've heard of it, okay? But of course, resistance is the opposition to the flow of electrons through a circuit. Yes, one of those concepts is hard to describe without using the word resistance itself. Like resistance is the fact that a material resists the flow of electricity through it. Like you don't want to use the word resistance in a different tense. The symbol for resistance is R, meaning like in an equation, the letter for an equation, and the unit is ohms. So then the symbol for the unit itself is omega, which is like Lululemon, of course, right? Originally it was resistance, still, just saying. Resistance is what causes electrical energy to be transferred to the material. So when we looked at circuits in the past and we had electrons being pushed along, and then like an energy just gets dropped off just on the load rather than throughout the rest of the circuit, that's because there's resistance in the light bulb, or resistance in the motor, or resistance in the device that's getting the energy. So in loads, it leads to, of course, the desired form, right? electricity, energy from battery, and it ends up as light, or it ends up as sound if it's a speaker, or motion if it's a motor, or heat if it's a heater. In wires, it just ends up as like wasted heat. We have, I think maybe both vacuums do it, but certainly our older vacuum. If you're using our older vacuum for a while, then you go and like unplug the cord and plug it in somewhere else, it'll actually be quite warm. So they probably should have used a little a wire with less resistance, let's say, for now. We're going to look at what that would mean. But if it was a wire with less resistance, then less energy would get dropped off in the wire, leaving more energy to get dropped off in the motor. Okay. So you think of like walking through the turnstiles, going into a store or into the subway in Toronto or whatever. There's a little bit of resistance there as you walk through, right? So you're transferring energy to that thing, and you feel a little bit of resistance as you go through it. That is an analogy, of course. I don't want you to think I'm telling you that there's turnstiles in an electric circuit, in a light bulb. Okay, but just talking holistically about resistance as a concept. Okay. So factors that affect resistance. What could Electrolux, the old vacuum we have, what could they have done with the wire to make it so it wouldn't heat up? Any guesses? What could they do with the wire to make it so that it doesn't heat up like it does? What are some factors that affect resistance? They could have made the wire blank.
Type of material it's made of?
Yeah, you're observant. Good job. So they could have made it out of like gold or silver or something, right? And that's one of these in here, probably. I'm giving away everything now. Type of material. I guess that's the first one. Type of material. So they could have made it out of something other than copper. But of course, copper is a pretty darn good conductor, right? So when we're talking about type of material, I didn't cover it up quite fast enough for Sarah. Talking about type of material, it just has to do with how freely the electrons can move within the material, right? Metals, of course, have low resistance, and because their outer orbits aren't full, a little bit of chemistry review there, right? And so copper is often used because it's an excellent conductor and it's nice and available and so on, not too expensive. Silver and gold are even better, but of course you're not going to have like a gold wire in your vacuum cleaner. They're expensive enough as it is. Let's put it that way. You haven't had the pleasure of buying a vacuum yet, but to get a good one, you're spending some money. You probably haven't anyways. It's more of a once you're moved out and married and you're like the exciting purchase of a vacuum. Remember those words. You'll actually probably, never mind. Anyways, type of material. What else could we do? So Electrolux isn't going to make the cord out of gold. Instead, they could do what? Any guesses? Should I just keep going? I don't hear any guesses. I'm going to keep going. They could make the wire thicker. Right? So if you have a cross-sectional area, if you make the wire thicker and thicker, then it just has less resistance. Right? So when you cut a wire, you look how thick it is. That's the cross-sectional area. Thicker wires have less resistance than thinner ones. Right? So electrons flowing through a thick wire think of it as like lots of room to move freely through. It's more of an analogy than anything, but it literally resists the flow of electricity less. In a water pipe, if you have a nice thick, like a big pipe, water flows more easily through it. All good analogies to help you think of thickness, just to help you remember that this is one of those factors, right? So that they could do that. I think why they don't, of course, is because the cord is designed to coil up inside the vacuum easily, and if it would be too stiff if they did that, right? So it is what it is. Like they made it the way they did, probably the best they could, right? Another factor is the length. Okay, the longer the cord is, the more resistance there is. I'll come back to that page in a second. The longer a cord is, the more resistance it's going to have. Okay, so if you're just making point form notes about this on a page, so in case I ask you anything about resistance at some point, it's fair game. Like it's very knowable things, let's say. You might just have a dash beside here saying like the longer a wire is, the more resistance it's going to have. All right. Think of it as like more atoms for electrons to be able to like dance their way through and force their way through, and more material to force their way through. So knowledge of that is really important when you're choosing extension cords for a job, right? The longer the extension cord is, then the more energy is going to get dropped on the wire along the way. So if you're using a high draw device like a table saw or a skill saw, or even worse, heaters draw a lot of energy. If a fair amount of the energy is being dropped off in the cord on the way to your device has a hard time doing its job because it doesn't have the energy left over like that it's supposed to have, right? So think of in a household circuit, 120 joules each coulomb has, right? 120 joules. So if 20 of those are dropped off on a long, skinny extension cord, then you're asking your table saw to cut through a big piece of wood with, approximately 20, it's less than that, but 18%, let's say, less energy than it's supposed to have. And so it's not going to work as well. It can actually damage things. in the circuits. So really long extension cords tend to be, if they're good ones, extra thick, right? So that they can handle the kind of current you might want to put through them, because they're going to have less resistance because of the thickness, cross-sectional area, to make up for the fact that they're long. And you'll see infographics, we call them, but you'll see information in various ways. So gauge, by the way, the smaller the number, the thicker the wire. Okay, the reason for that is back in Britain, sometime whenever it was, they took a pound of lead and they melted it, and if you take a pound of lead and pour it into 12 equal size spheres, then that's the size of a 12 gauge wire and also a 12 gauge shotgun. If you put the pound of lead into 20 little equal spheres, then that's the size of a 20 gauge wire, and so on. Okay, so 14 gauge is really common in household wiring. If you need a little more current for a circuit, you want to have more capabilities in the circuit and less resistance, so when you go with a 12 gauge, or I think our hot tub might have been like the one I wired up might have been like 6 or 4 or something like that gauge, just because it needs to carry more current. So you can see here, if you have this gauge, this length, you can only carry this many amps, and so on. There's different ways that companies try to help you make a good choice, other than just buying an extension cord based on the price, because of course you end up wrecking things. Your motor can just burn out on your device, or the brake that in a miter saw, when you let go of the trigger, the blade stops. That brake tends to die first if you don't have enough current, or enough voltage, I should say, because a lot of voltage dropped in the line. And my dad. Go ahead.
Sorry. What about the flat wires? And it looks like they're two put together. What would that be?
So the flat wires and two put together thing, I think you're talking about I'll just do a Google search here, like a 12. I'm going to do a 14.3 wire. You mean like this? It's coming up here, I think. There was a little picture there, but you mean, I don't know how much bigger the picture's going to be, if it's worth the wait or not. Come on. Holy, like that you mean?
Yeah.
So what that is, that's a 14 gauge wire, that's another 14 gauge wire, and then that's another 14 gauge wire. And so what you have in a household circuit is that's your hot wire. That's the one that has like the high voltage, the 120 volts. The electrons essentially get pushed and pulled from this wire, and then they push and pull into this one. That's your common. And then this is your safety wire. That's your ground wire. And so electricity wants to go from here to here and back and forth between these two. If this wire, or actually this wire, if this wire broke inside your box, inside your electrical box in your house, and was sitting against the electrical box, it would ground out to this one and blow the fuse. So that's your safety wire. It's called your ground, or your ground. Does that answer your question enough?
Yeah, thank you.
Yeah, and so the thicker you get like a 14 gauge wire, then they would be like thicker. They'd just be thicker copper inside of there. Yeah, so that's what's inside of there. Great question. So then, yeah, the thicker the wire, the more current you can carry. A little side note about the thickness stuff. If you ever get into like car stereos and so on, you have to get a wire that has a small enough amount of resistance that by the time that wire goes from the battery in the front of the car all the way to your amplifier in the trunk of your car, it has enough voltage to let the amplifier do its job, right? So if wires have too much resistance because you hooked it up with a thin wire, or cheap wires are made out of aluminum, either way you're dropping some voltage across them. Your device actually insists on getting the amount of energy that it needs. Okay, like an amplifier has electronics in it, and it'll insist it gets the amount of energy it needs. So if it's not getting the energy, like if each coulomb isn't delivering 12 volts, instead it's only delivering like 10 volts, then what's the solution? It's going to demand more current, right? So the amp demands more current in order to get enough energy. So a whole bunch of groups of 10 joules rather than less groups of 12 joules. Makes sense, right? You're going to get the same amount of energy. So what happens inside of an amp is the increased current means that more heat builds up inside of the amp and actually causes the amp to melt. So when you say you like burn out an amplifier, it's literal. Like it's actually a piece inside of it got so hot that it burnt the plastic around it, melted the wiring, and your amp stops working. Okay, that's why people pay for big, thick power wires to run a car stereo amplifier, because you paid for the wires, and then your amplifier lasts instead of burning out. The amplifier in my boat died because the connector that the marina that hooked it up used was corroding inside. It wasn't a very good connector, and so there was voltage loss on the connector that they had used for the wire to connect to the battery. And yeah, so the amp died, and then I put a new amp in, and then after a while that amp wasn't working. But luckily, when I was testing, actually I think what it was, I went to put a fused link in there, a circuit breaker in it, and when I was testing the voltage in that, it was basically no voltage on the outside of the connector, right? So the amplifier, the one that died, was drawing more and more current to try and work properly. Anyways, so the other one is weird. It's temperature. And it turns out that the colder a wire is, the less resistance there is, which I think a lot of people think the other way around. But the colder a wire is, the less resistance there is. These videos, I'm not going to bother showing them, but they're basically show the resistance of a wire, a coil of wire, and they put it in liquid nitrogen to cool it down, and the total resistance of that coil of wire drops as it gets colder. So I like to think of it as the kinetic molecular theory of heat. And so if the wires are hot, then the atoms are vibrating around, and it's a big chaotic mess, and it's sort of harder to get the electrons to flow in a nice even way. It's more of an analogy than a reason, but it certainly helps me remember it. Okay, so colder on a colder day, technically your extension cord is doing a better job on a cold day. That seems like it's counter to what you experience in life, though, because there's a lot of things that don't work as good on a cold day. Like cars don't start as easily on a cold day, for example, but that's not because of the wires. That's actually because of the oil inside the engine being as thick as molasses, and the battery, the chemicals inside the battery aren't doing their chemical reaction as well because they're so cold, and there's a lot of other factors. Okay. Resistance is measured with an ohm meter. Remember the value you're measuring is ohms, so they call it an ohm meter, and it has the omega symbol. So I've used an ohm meter lots and lots of times. Specific examples, when I put in-floor heating in the house, I had to check the resistance of the line and see that it matched the factory specs. If it was same as factory specs, then you know it's not damaged and you're good to go in installing it. There was a position sensor in a washing machine that had died, that I had to check the resistance across the green and the white wire and so on. And if it was a certain value, then it's good. And if it was not the right value, you know it's bad. And so we knew to order a new part for the washer and got it working. That was good research on Mrs. Horn's part. She was Googling and she told me about the parts, and I took the tools and went in and checked the resistance, and sure enough, it was wrong as the website or wherever it was on the internet indicated. So we ordered a part and fixed it for like $20. It was great. Yeah, so the locked. Oh, I don't know why that's locked there if it's not there, but the equation for resistance is, I guess I'll just do that. It depends on the type of material and the cross-sectional area and the length and so on. We're not going to use the equation a lot, but resistance as a result is like, if it's longer, there's more resistance. That's why that number's in the top. If that's a bigger number, it makes this R be bigger. If the area, cross-sectional area, the size of the wire is bigger, it makes the resistance less. So it makes sense to be dividing by that one. And then the rho symbol here looks kind of like a curly P or whatever. That's the type of material. So that's the resistivity of the wire. And there's just numbers you can Google, like what's the resistivity of aluminum? What's the resistivity of copper, and so on. And you can calculate the resistance, but it's not a huge focus of the course by any means. But I just wanted to show you that it makes sense and exists and so on. So you calculate, area and so on, and then so calculate the area first. They have it worked out for you, and then you plug the number in and get the resistance. So if you had the equation, you just plug numbers in, right? Okay, so that's resistance as a concept. Do you have that one as a? Yeah, you do. So you have that handout as well. So that'll help make up for that day where we didn't do anything on the first day, I suppose. But so you've got this table here for resistivities and then calculations questions. So that leaves us with 20 minutes remaining in class for you to work on questions and ask for help. So I went a little more than I normally will in a class there, but we went less than we would have on 2 other days. So I think it averages out, if you will. Okay, so I will post as many of the solutions as I can for that stuff. I might just not post every single one, and I would kind of think the same for you in doing it as well. In the past, I've described homework checks as like totally complete, incomplete, or not done, right? But for a class like this, if there's repetitive questions, another option for a homework check, obviously I'm not checking right now, but because of our situation, but IS, incomplete because you're skipping, makes total sense to me. If there's 6 questions that are all the same and you do a couple of them and you look at the questions and see that they're the same type, it's just more practice, and you feel like you're good to go on the skill, do some of them, right? You don't need to do all of them necessarily, but it's totally up to you, right, to decide how many you need to do. Okay, I just thought I'd mention that because I know there's a number of questions assigned now for us, but so make sure to practice some voltage ones, make sure to practice some current ones, and make sure to do some resistance ones. Enough that you feel like you're good to go on those skills. All right. I barely see my head. Any questions? I know there's a chat going on here, but what's the chat? I don't answer these questions during the lesson by any means, as I've told you, but oh, Dawson's here. Good. Good. I was going to check the attendance from the meeting record. Welcome aboard, Dawson. Are you here still right now, like to talk? Hi, conversation. Show participants. That's what I want to do. There we go. Yeah, he's there. Say hi, Dawson.
Hello.
Hey, so you're good to go for tech and whatnot for doing the course?
Yeah. I'm just on my laptop, so I don't have a microphone on my laptop.
Oh, so it's a little hard for you to say
Yeah.
stuff.
Yeah, I went on my phone real quick.
Yeah, perfect. There's just no better way to say hi to someone than to actually. So that's good. Thank you for doing that for me. And I just want
Of course.
confirmation from you that you're good to go, and let me
Yep.
know. You'll let me know if you need anything from me for getting through the course and so on, right?
Absolutely.
Perfect. Good stuff.
Awesome. Thank you.
Yeah, thank you. All right. So I will do attendance, and you guys can start working and ask for help if you need. Somewhere here, I should print out a attendance list. Oh, well. That's my sheet. There it is. Still Jeremy Simpson. Anybody know anything about Jeremy Simpson? He said he emailed me that he was good to go, but it's 2 in a row now. Oh, looks like that explains it. All right. So although of course I recommend you work on the questions now, and so you can ask for help if you need it and so on. I'm done teaching, and so if you decide you want to do the work later, you can log off if you want, if you're hungry or whatever. But I'll certainly stay online with you until everybody's logged out at the very least. And I'm still monitoring email during the rest of the day and all that too, so it's all good.
Has the resistance lesson been uploaded yet?
No, I'll be saving and posting that stuff. You have handouts to do with it, but I'll start saving that stuff right now and posting it.
Okay, thank you. I think I just missed part of it when I was out of the meeting.
Okay. Yeah. Oh, and I should end my recording here. Stop recording.
Mr. Horn, I was just wondering, for the equation for electrical resistance, does the area have to be in like a specific unit?
Just check to make sure here. Yeah, because I would think it would just go with SI units. Where was it? Up here. So it doesn't say on that one, does it? But it's going to say in the example.
Yeah, because it says on one of the questions it has a diameter of 2.0 millimeters. I was wondering if I had to change that at all.
Yeah. I would have sort of thought that it would be like meters, but meters is pretty big in comparison to the value. So I think what you're going to do is you're going to look at what they tell you. So they're saying resistivity here is ohms and meters. Yeah, so that one's meters. Yeah, these numbers are meters. Yeah, so meters.
All right, thanks.
Yeah. So think of it's actually dimensions squared, right? And so if you had centimeters to go to meters, think of what you'd have to multiply by, which would be divide by 100. And so you'd be dividing by 100 twice. That makes sense, right? Or you can just, if you have your radius, of course, you can just convert it to meters, and then as part of your square, of course, you're converting it to meters twice, essentially, when you're squaring it. So in this example, it's worked out. Did they? Because it was given in diameters in centimeters. Yeah. See, they're converting it to meters right there. Yeah. So they convert it to meters and then put it in. So, and I remember seeing centimeters there, so I was wondering like, why they wouldn't be doing it in centimeters? Were they? And so I was waiting to sort of decide officially here, but yeah, it's meters, of course. SI units, meters, kilograms, seconds.
All right, perfect.
All right, lesson 4, export as.
Mr. Horn, I'm not sure if you care, but I think the recording's still going.
Yeah, I was just actually going to go and do that. Thank you. I definitely do care because